Next time you are sitting in traffic on the highway, do something most drivers never bother to do. Look at the trucks around you. Not the cab, not the trailer, not the load. Look at the wheels. All the way at the back, beneath the rear of the trailer or the truck body, you will occasionally see something that looks genuinely wrong. A set of wheels, a full axle with 2 tires on each side hovering in the air, not touching the road, just spinning slowly in the breeze, a few inches above the asphalt, as the truck rolls along at highway speed. Your brain registers it immediately as a malfunction. Something has failed. A suspension has collapsed. A hydraulic line has burst. Surely the driver does not know. Surely someone should call someone. You might even feel a brief impulse to honk, to wave, to somehow alert the driver to what appears to be a serious mechanical emergency happening beneath his own vehicle. But the driver knows exactly what is happening. He made it happen himself, with a single switch on his dashboard. And those wheels hovering in the air are not a sign that something has gone wrong. They are a sign that everything is going exactly right. That floating axle is one of the most intelligent, most deliberately engineered features on any heavy vehicle on the road today, and almost nobody outside the trucking industry has any idea what it is for or why it exists. Welcome to Normal Things' Crazy Origins. Today we are uncovering the truth behind those ghost wheels on heavy trucks, what they are called, how they work, and why a system that looks like a catastrophic failure is actually a masterpiece of engineering logic that saves the trucking industry billions of dollars every single year. To understand why some truck wheels are designed to leave the ground, you first have to understand the enemy they are fighting. And that enemy is not mechanical, it is mathematical. Specifically, it is the physics of pressure, weight distribution, and the surprisingly fragile relationship between a heavy vehicle and the road surface beneath it. Roads look solid, they feel solid. But concrete and asphalt are, in engineering terms, relatively brittle materials with defined load limits. They are not designed to withstand unlimited weight at a single point. They are designed to handle weight that is spread across a sufficient area. The critical measurement is not total vehicle weight, it is axle load. The weight pressing down on any single axle, divided between however many wheels that axle carries, determines the pressure applied to the road surface at any given point. Governments around the world have established strict legal axle weight limits, precisely because engineers understand that exceeding those limits does not just wear roads down, gradually it fractures and destroys them rapidly, creating repair costs that run into billions of dollars annually and are ultimately paid by taxpayers. Now consider a fully loaded dump truck carrying 20 tons of gravel, or a concrete mixer at full capacity, or a flatbed hauling heavy construction machinery. The total weight of the vehicle and its load is enormous, sometimes pushing the upper boundaries of what is legally permitted on public roads. If all of that weight is concentrated on just 2 or 3 standard axles, the load per axle almost certainly exceeds the legal limit, and the pressure applied to the road surface at each wheel contact point becomes genuinely destructive. This is where the lift axle, the floating wheel you spotted from your car, enters the picture. Think of it this way. Imagine trying to walk across a freshly laid wooden floor in stiletto heels. Your entire body weight concentrates through that tiny heel tip into a minuscule contact area, and the pressure per square centimeter is enormous. The floor dents, cracks, or collapses entirely. Now put on a wide, flat pair of snow boots. Suddenly your weight spreads across a much larger contact area. The pressure per square centimeter drops dramatically. The floor holds. You cross safely. The lift axle is the truck's snow boot. When the driver flips the switch to deploy it, a set of powerful airbags inflates, pushing the additional axle downward until its wheels make firm contact with the road. Suddenly, the truck's total weight is distributed across more axles, more wheels, and a larger total contact area. The load per axle drops. The pressure per square meter of road surface drops. The truck moves from being a stiletto heel to being a snowshoe. It becomes legal, it becomes compliant, and it stops destroying the road beneath it. The engineering of the lift axle itself is elegantly simple. The axle is mounted on a hinged mechanism attached to the truck's frame or the trailer chassis. In its raised position, powerful springs hold it up off the ground. When the driver activates it, a dedicated air compressor, drawing from the same pressurized air system that operates the truck's brakes, inflates a set of rubber airbags positioned above the axle. As the bags fill with air, they expand downward, pushing against the axle assembly and forcing the wheels toward the road with controlled, adjustable force. The pressure in the airbags can be precisely calibrated, which means the downward force on the lift axle, and therefore its contribution to load distribution, can be fine-tuned depending on the actual weight being carried. When the driver wants to raise the axle again, a valve releases the air from the bags, the mechanism pulls the axle back up, and within seconds, the wheels are hovering clear of the road once more. But here is the question that immediately presents itself. If more wheels touching the ground means better weight distribution and safer roads, why not simply keep all the wheels down all the time? Why go to the mechanical complexity and expense of designing an axle that can be raised and lowered? Why not just weld it down and leave it? The answer, as is so often the case in engineering, comes down to economics, and the economics are not subtle. Every tire that rolls in contact with the road surface generates what engineers call rolling resistance. The rubber deforms slightly with every rotation, gripping the asphalt, and overcoming that grip requires energy. That energy comes from the engine, which burns fuel. The more tires you have in contact with the road, the more rolling resistance you generate, and the harder the engine has to work to maintain speed. On a fully loaded truck where every axle is earning its keep by distributing genuine weight, this rolling resistance is a necessary cost of doing business. But on an empty or lightly loaded truck, those extra axles are not distributing any meaningful weight. They are simply adding rolling resistance and burning fuel for no engineering reason whatsoever. By lifting the axle when the truck is running empty or at a light load, the driver eliminates that unnecessary rolling resistance instantly. The engine works less hard. Fuel consumption drops measurably. On a truck covering hundreds of thousands of kilometers per year, this fuel saving is not trivial. It translates into thousands of dollars of operating costs saved per vehicle per year, multiplied across an entire fleet of vehicles doing the same routes day after day. Tire wear is the second major cost that the lift axle addresses. Heavy truck tires are extraordinarily expensive. A single tire on a large commercial vehicle can cost several $100s, and a full set across multiple axles represents a significant capital investment. Every kilometer a tire spends in contact with the road surface wears it down. An unnecessary axle left deployed when the truck is empty is grinding expensive rubber against asphalt for no purpose, shortening tire life and advancing the date of an expensive replacement. Raising the axle when it is not needed preserves the tires for when they are actually doing useful work, dramatically extending their operational life and reducing replacement frequency across the entire fleet. Then there is the question of road tolls. And this is where the story takes a turn that reveals just how precisely the trucking industry has learned to exploit the lift axle's flexibility. Across many highway systems, bridges, and tunnels around the world, toll charges for heavy vehicles are calculated not by total vehicle weight, but by the number of axles currently in contact with the road. The logic behind this toll structure is that more axles generally indicate a heavier vehicle causing more road wear. But a truck with a lift axle raised presents fewer axles to the toll plaza than the same truck with the axle deployed. By lifting the axle before reaching a toll point, a driver can legally reclassify the truck into a lower toll bracket, sometimes reducing the fee by a significant percentage. Across thousands of toll transactions per year on a busy route, this saving accumulates into a substantial operational advantage. It is entirely legal, it is widely practiced, and it is one of the reasons that lift axles became standard equipment on so many heavy vehicles once operators understood the full financial picture. The fourth reason for the lift axle is the one that surprises most people when they first hear it, because it has nothing to do with weight or money. It is about geometry and the basic physics of how a long vehicle turns a corner. Any vehicle with multiple axles has a turning problem. When you steer the front wheels of a truck to the left, the rear of the vehicle does not simply follow, it swings outward to the right in what is called off-tracking. The longer the vehicle and the more axles it has, the more severe this off-tracking becomes. Now add to this the behavior of a fixed rear axle during a turn. As the truck pivots around a corner, the rear wheels are not aligned with the direction of travel. Instead of rolling forward cleanly, they are being dragged sideways across the road surface. This lateral scrubbing the tire, fighting against a direction of movement it was not designed to accept, generates enormous friction. It produces that distinctive screaming sound you sometimes hear from large trucks taking tight turns. It shreds tire rubber at a savage rate. It puts massive lateral stress on the axle bearings, the suspension components, and the truck's frame. And critically, it makes the truck resist turning. The more fixed axles you have dragging sideways across the pavement, the more the truck wants to continue in a straight line, and the harder it becomes to navigate a tight corner, a roundabout, or an urban delivery point. By lifting the rear axle before attempting a tight maneuver, the driver effectively shortens the truck's wheelbase. With fewer axles in contact with the road, the off-tracking is reduced, the scrubbing disappears, the turning radius tightens, and the truck becomes a fundamentally more maneuverable vehicle. It is, in effect, a machine that can reshape itself depending on what the road demands of it. What makes the lift axle so remarkable as an engineering solution is that it addresses four completely different problems: legal compliance, fuel efficiency, tire economics, and vehicle maneuverability with a single, mechanically simple, driver-controlled system. It is the kind of elegant engineering that only becomes visible when you understand all the constraints it is simultaneously satisfying. A naive observer sees a broken wheel floating in the air. An engineer sees a load balancing mechanism, a fuel management tool, a toll optimization system, and a geometry adjustment device, all rolled into one switch on the dashboard. So the next time you are sitting in traffic and you spot those ghost wheels hovering above the asphalt on the truck beside you, you will know the full story. The driver is not unaware of a suspension failure. He is not carelessly ignoring a mechanical problem. He has made a deliberate, informed decision to lift that axle because his truck is running light, his fuel meter is ticking, his tires are expensive, and perhaps because there is a tight turn coming up that will go a lot more smoothly without extra rubber dragging across the pavement. That floating wheel is not a sign that something has broken. It is a sign that the system is working exactly as it was designed to, intelligently, efficiently, and invisibly, to everyone who does not know where to look. If you enjoyed this journey into the hidden engineering of the road, hit that like button, share this video with someone who has seen those floating wheels and wondered what went wrong, and subscribe to Normal Things Crazy Origins for more stories about the everyday world that are far more remarkable than they appear. Because the most extraordinary engineering is always the kind that looks, at first glance, like a mistake.